See you there. I'm just hitting the links today. I've had some time on my hands. And so, it's good to see you folks. I'm your AP Stats teacher, Mr. French. So what we're going to be doing today is a full chi-squared test for homogeneity. In the last video, we talked about the test statistic. We talked about how to calculate the expected values, and we did a little bit of calculator work as well to get all of those expected counts. So we're going to be doing two examples on a chi-squared test for homogeneity, which is only used for two-way tables. Let's go ahead and get started. We are going to be doing a full chi-square test for homogeneity today. Our first example is going to be talking about python eggs. So here's the situation. How is the hatching of water python eggs influenced by the temperature of the snake's nest? Researchers randomly assigned newly laid eggs to one of three water temperatures: hot, neutral, or cold. Hot duplicates the extra warmth provided by the mother python. Cold duplicates the absence of the mother. Here is the data on the number of eggs that hatched and the ones that didn't hatch. So this was an experiment determining if the temperature of the nest influenced how many python eggs hatched in that particular temperature. So we have water temperature and we have hatched. It's either they did or they didn't. Cold, neutral, and hot. So we have three separate populations. If we were to just kind of eyeball this, it looks like, with the cold, it's pretty close. It's only a difference of 5. With the neutral, it's a much larger difference. With the hot, certainly we have the most with the hot. What you would do is you would take a look at the proportions. So in this case here, under the cold, if you were to do the calculation here, under the cold, about 59% of them hatched, a little bit more than half. Under the neutral, about 67% hatched, and under the hot, about 72% of these ones hatched. So here's the question that we're going to be asking, and it's the question that a chi-squared test for homogeneity asks: are the differences between the three groups statistically significant? In other words, does the temperature of the nest really influence the proportion that would hatch, or could these have happened simply by chance alone? In other words, we had a total, so 129 python eggs hatched in general. If we were to calculate the totals here, 129 of the eggs hatched out of 187, so we're kind of curious as to how likely is it that the temperature is actually doing something versus that regardless of the water temperature that 129 eggs are going to hatch no matter what category they were randomly assigned to. Once again, these are random assignment. These are separate populations of temperatures here. If you have separate populations and you're asking whether or not the treatment is effective amongst these separate populations, that is a test for homogeneity. So what we're going to do is we are going to set up our null and alternative hypothesis. We're going to go through the 4-step process here. So our state in a test for homogeneity, in any type of chi-squared test for homogeneity, the null hypothesis is that you were going to say that the distribution amongst the water temperatures are truly the same, versus the alternative is that the distribution of water temperatures affecting the hatched eggs is not the same, right? So this was about 50%, this was about 60%, this was about 70%. So obviously we have some data to suggest that maybe the temperature does influence. So we're going to say that the null hypothesis is that there is no difference in the distribution of eggs that hatch in cold, neutral, or hot water. The alternative hypothesis is simply that, well, if we are assuming that there is no difference in these three distributions, the alternative is that there may be some sort of difference in these distributions. So all we'll put is there is a difference in the distribution of eggs that hatch in cold, neutral, or hot water. And so our state is done. We're gonna move on to the plan. So I'm gonna put the title of this type of test. We are gonna do a chi-squared test for homogeneity. A chi-squared test for homogeneity looks at 3 separate populations or 3 separate treatments, or a chi-squared test for homogeneity looks at separate populations or separate treatments and asks if the distribution amongst those treatments or populations is the same or not. So I'm going to put the title of this test here. We have our random. So random is always going to be a part of our conditions. In this case here, it was a randomized experiment. They were randomly assigned to the different temperatures. So 3 groups in a randomized experiment. The 10% rule in this case isn't necessary because once again we're doing an experiment. So it doesn't say that we did any sampling. We just they were newly laid eggs. So there was not random selection because the eggs were just newly laid in this case. Well, it's not necessarily random. So there wasn't a random selection because the eggs were newly laid. And then the large counts. So the large counts is that all expected counts need to be at least 5. So there's 2 ways to get the expected counts. What I could do is I could take every single one of these observations here, so an observation of 16, I would take the row total times the column total of 27 and divide by 187. So I would have to do the expected counts for 16. I would do 129 times 27 divided by 187. I would do the same thing for the next one. So 38's expected count would be the row total of 129 times the column total of 56 divided by the total of 187. And I would have to go on and do that for every single of the 6 observed results. Honestly, I don't really want to do that. So what I can do is I can go to the calculator and just list out the expected counts there instead. So here is some calculator work one more time to get expected counts for a 2-way table. What you're going to do is you're going to click second and then matrix, go over to edit. We have a 2 by 3. There's 2 rows and 3 columns. This is a 2 by 3. And I'm just going to copy the 2-way table into my calculator by pressing enter. Since I have this table already in my calculator, I'm going to go to Stat, Tests. This is not a goodness of fit. Remember, a goodness of fit, there's a claimed distribution. All you're seeing is if a distribution matches some sort of claimed distribution. In this one, you have separate distributions. You have multiple distributions, and you're checking to see if these multiple distributions are the same. So you have a multiple comparison here. That's just your typical chi-squared test. Observed will go into A. We already put that there. The expected is going to be inputted into B, and we're going to calculate. So I've calculated. Now, some of you may be asking, why have you done the calculation? Well, it's because now you've calculated it. Remember that when we do this part, it's going to put all the expected counts into B, and then we can just pull up the matrix B and check to see if all the expected counts are at least 5. So I'm going to do that. So I've calculated it. Okay, it's done. I'm going to go to second matrix again, and now B has something in it, and I'll just press enter. And now I can make a little list of all these values and say that they're all at least 5. Good to go here. So I'll just write that down here for our step. So these were the expected counts, and they're all at least 5. Plan step is now done. Reminder, your large counts conditions are always going to be different for different tests, so be really mindful that you understand which large counts conditions are met for different tests. So now we'll do the do step. Doing the do. I'm going to use some of these values here, so we got to show a little bit of work. So I'm going to use some of these values, like 16, and I can look at its expected count, 18.62. So I'll just do 2 of these, and it doesn't matter which order, just so long as you show me or you show the person grading this that you're doing the correct calculation. So I'm going to say that we have a chi-squared that is equal to the observed So I'll start with the 16. So the observed for 16, so the observed minus what we would expect, which is 18.63 squared over 18.63 plus, I'll say 38 minus its expected, which is very close, 38.61 squared over 38.61. And don't forget that dot, dot, dot. So now, put the dot, dot, dot. I don't want to just do this in all my calculators, so I'll go to test, go all the way down just to chi-squared. I'm going to calculate, and I'll just say that it equals, this value here of 1.7. We have a p-value that is equal to 0.4267, and we have degrees of freedom equal to 2. Now remember, you should be prepared for this. There's going to be multiple choice questions that ask you about the degrees of freedom for a chi-squared test. Remember that degrees of freedom come from the row categories minus 1 times the column categories minus 1. And so in this case here, the number of rows was 2, and the number of columns was 3. Columns are up and down. Rows are side to side. So this is 1 times 2. Be on the lookout for multiple choice questions later on, stuff like that. So our degrees of freedom for this test were 2. That's why you have this number here. Cool. So now what we have is our work with our test statistic. We have a p-value, and we have our degrees of freedom. Make sure you have all 3 of those things. Now it's time for the conclude. So because the p-value of 0.4267 is greater than alpha equals 0.05, we fail to reject the null. We do not have convincing evidence that there is a difference in the distributions of hatching python eggs for different temperatures of cold, neutral, and hot. So even though there was a difference in the distributions of cold, neutral, and hot, remember that this was about 59%, this was about 67-ish%, and this was about 72%. So out of the total here, so about out of these 27 that got cold water, 59% of them hatched. Out of the 56 that got neutral water, 67 of those 56 hatched. And out of the total of hot water, so out of the 104, 72% of those hatched. So even though these distributions were different, we don't have convincing evidence that they were different enough. So we failed to reject the null. We're not convinced that the temperature in this experiment had a significant influence on the hatching rate. Just a heads up, a little reminder here, chi-squared tests only work with counts. They only work with counts. Remember, it's observed minus expected squared over expected. None of these are going to be proportions ever, so don't ever use proportions in a chi-squared test. Be it a goodness of fit, be it a test for homogeneity. The next test that we're going to look at is something called a chi-squared test for independence. It's essentially the same exact test. The only things that are different are the hypotheses and the conclusion. I lied to you in the beginning of the video. We're only going to do this one example. If you have questions on other examples, feel free to email me those questions, or you can put them on the Google Classroom as well. Under that particular video would be very helpful. Then I can respond to your questions there. Hey, let's do that. I'm going to post this on the Google Classroom. There'll be a little announcement. I want you to, if you have any questions about this video, be sure to post them on the Google Classroom. And you can comment, and I'll comment back, and I'll answer your questions in the order that they come in. If you have 5 questions, feel free to put all 5 questions there. I'll do my best to answer them as I can. And for those of you that want me to answer all the even questions, I'm not going to do that. No, I don't want to do that. Thanks for your flexibility. Thanks for your time. And happy St. Patrick's Day.